and a very friendly person. So it's good to have him as a colleague and also as a good friend. So with that introduction, I'm going to stop sharing, and then I will let Professor Bora Cetin to share his screen and start his presentation.
Thank you very much for your kind words, Krishna, Dr. Reddy. I really appreciate it. Same kind words goes to you. I really appreciate Dr. Krishna. I was an assistant since I get into this business. Dr. Krishna Reddy was very supportive of me, and I really appreciate his support since the beginning of my career. I really appreciate it. And again, thank you very much for this opportunity too, Dr. Reddy, giving me a chance to talk on this webinar series. I think they're, like you mentioned, they're really very useful and informative and allow us to communicate with each other in this area globally, not only regionally. So I really appreciate the opportunity. And
Bora, can you put your video on? Just it would be nice to see the person talking.
Sure.
Yeah.
Absolutely.
I will hide my video. You can.
Okay. It should be on now, I assume, right? Let me check. All right. Everybody sees it. Okay. So again, Dr. Reddy, thank you very much for opportunity, and thank you very much everybody for being here and willing to listen to today's presentation. Today I will talk about use of recycled materials in pavement geotechnics, and I have conducted field tests on recycled materials that are used in pavement foundation systems. Different, and my major focus today will be on use of recycled concrete aggregate and recycled asphalt pavement materials in pavement foundation systems. Look into their field performance, restore durability, and then environmental impacts. I look into the environmental impact of these use of these recycled concrete aggregates in terms of pH, metal contamination, and geochemical modeling to the environment. What are their impacts? And again, if we Dr. Reddy already described my academic and professional background. I earned my Bachelor of Science degree in Civil Engineering in 2007 from Istanbul Technical University in Turkey, and joined to graduate program in the Department of Civil and Environmental Engineering at University of Maryland at College Park. I did my MS, Master of Science degree there, and then continued to do my PhD. And when I graduated in 2012, I was lucky enough to get a faculty position. And started at South Dakota, then moved to Georgia, and I was at Iowa State for a while. And then 2 years ago, just like Dr. Reddy mentioned, I've been at Michigan State University. And the research, to this type of seminar talks, I first wanted to start with why I'm in this business, what my research program overly mainly cover. So I call my geotechnical material, my research group has a sustainable geotechnical infrastructure geomaterials research group. And in this research program, one of my main focus is on design and construction infrastructure with recycled materials, which will be the main talk, main topic of today's seminar talk. And then when we first do this test, I look into two things. The first thing, when I try to integrate any type of industrial byproduct there in payment systems or transportation infrastructure systems, I look into their geomechanical performance and then environmental impact. If it doesn't have an environmental impact, does it have concerning leachates, or it's environmental safe, then in that case, does it have good improvement in terms of geomechanical performance of these geomaterials. And then all of these geomechanical performance and environmental impact, first I evaluate them in the laboratory, then we get into the testing these materials in pavement in the field in situ conditions. Okay, and from there I look into the impact of climatic conditions, both in the laboratory and in the field. Like since we are I've been doing in research most of the time in the northern plains of United States, which the area is exposed to freezing and thawing cycles significantly. That impacts the characteristics of these recycled materials significantly. So I focus on that climate inputs, especially the freezing and thawing cycles. And then the last few years, I tried to use some smart materials into transportation infrastructure systems, and how would that impact improve the freeze-thaw durability of materials. And last few years, I also focus on a little bit on the engineering education and how we can use this research outcome that I described before integrated in the engineering education. And one thing that we do in the field, especially we're trying to do this the data-driven models. You need a lot of data to develop the data-driven models to predict the soil temperature, number of freeze-thaw cycles within the pavement foundation systems, or in general in soil systems. You collect tons of data, and how you analyze it and how you manage that data, we are also trying to cover that. So if you're doing any sustainable geotechnical engineering infrastructure system, these we recommend that as your main component of your research group. So what was my motivation to get into this? Because sustainability is a big word. It has been maybe last 20 years and still is a big issue and important characteristics, important word today. There are a lot of definitions of sustainability. It is capacity to endure in general and capable of being continued with minimal long-term effect on the environment. And like I said, there are several definitions of sustainability, but one overall acceptance of definition of sustainability is that you make a design, you build something that has to be resilient, that has to perform good, but it has to be environmental friendly, it has to be economical, and society should accept that material or that design. So where these three components come together, this is what basically you call sustainability. And why this was the motivation, and I asked, why is sustainability important? World overall, the earth that we live on has limited resources, and the needs of the people are unlimited. And this plot here shows the increase in the world population in beginning of 20th century, when the world population was only $2 billion. By 2000, it kind of tripled the amount of world population, come to the 6 billion. And it's projected to be at least between 10 to 12 billion by 2050. And one of the things as a result of it, what comes, and sustainability is directly related to this, for instance, electricity generation. Like because you have more people, you require more energy and you require more electricity, for instance. And in 1950s, the amount of electricity, net electricity generation, was almost 20 tetrawatt hours. And in 2000, this almost 1.5 times higher. And by 2050, it will reach to 60 TW hour, like tetrawatt hour. Okay, and where will this energy come from? In 2017, 4 years ago, this changed a little bit. Coal amount decreased a little bit, and more gas and renewable energy distribution increased. Like as you can see, we get the energies, and these numbers are for United States per se specifically. These in different part of the country, in different part of globe, coal is still a big energy source in certain countries, but in United States, its amount that it contributes to the energy consumption decreases every year. And in 2017, this is the energy resources where the resources that are used to produce energy. As opposed in 2050, we still have coal, but as you can see, we still need energies, and renewable energy is expected to gain increase along with the natural gas. But coal, as you can see, is still being used. I'm not going to talk about use of coal fly ash as a recycled material here, but what I'm trying to show here, with these energy resources, there will be always waste material that may be also useful, and then we use that in our payment foundation systems. And this, again, the top upper left corner shows the coal combustion byproducts that we got already piled up annually. Actually, these numbers are annual numbers. I'm not even talking about the landfill fly ashes. And as you can see, even in 2050, we will have more coal combustion byproducts. And also we have other wastes like tire waste, slag waste, construction and demolition waste. And these are the some of the numbers, how it changes even in 2 decades. And in 3 decades from now on, we will expect to have more tire waste, construction and demolition waste, and slag waste. So what are we going to do with these wastes? We keep placed like they are, most of them are currently placed in the landfills, and we will keep building these waste materials. We can't really replace them with any other materials at the moment. We need tires, we need iron products, we need wood products, and we keep building these landfills up to what level, and we need to do something about these waste materials if we need to find a beneficial reuse of these materials. So the question, what motivated me to get into this research area, how can we reuse these byproducts? And using them in transportation infrastructure, such as in payment foundation system, pose great potential to be used. So this is a typical schematic diagram of a conventional roadway construction. You have asphalt layer or concrete layer, and then you have a base course and sub base. And typically base course are built with conventional aggregates that you excavate and mine from quarries, aggregate quarries, and then you use them. And even then you use them, the payments most of the time fail prematurely, because majority of these based on the quality of these aggregate quarries that you collected and mined. And these are natural resources, and high quality aggregate quarries and natural resources are depleting every year. And that's another challenge. The figure on the left shows the annual aggregate production in United States. As you can see, in 2006, this was close to 500 million tons. And in 2011, this come to the 1 billion tons of aggregate in 2011. And now US infrastructure aged quite a bit. And then we needed more in 2019, and today in 2021 we needed more aggregates to replace this aged infrastructure. Of course, this comes with costs, and like I said, we have very limited high quality natural aggregate resources, and we have been using aggregates for 100 years in construction, and we need to replace these natural resources with other materials. This is another map that shows how the northern plains of United States changes, have the lowest quality. The shaded area, glaciated Midwest, for instance, had the lowest quality aggregate sources. And this becomes a significant challenge in building roadways. Therefore, in this area, in this part of the United States, you really wanted to replace these conventional aggregates that you mined with something more durable and more stronger. And recycled concrete aggregate and recycled asphalt pavement pose great potential to be used in such application. Here again, these are the numbers that how much annual concrete waste is produced annually in the United States and how it increased because of the aging infrastructure. So same with the concrete asphalt waste. And there are a lot of road waste, that aged roads that are reclaimed and ready to be used. And also the building waste, a lot of demolished structures and all that. So this poses great potential instead of keeping them in a landfill or in somewhere middle of nowhere that no cover, nothing in a stockpile there. How about we try to use this in pavement foundation systems? And when we get to this recycled concrete aggregate, recycled asphalt pavements, what are the challenges? So these can be used to replace conventional aggregates and pavement foundation systems. And what are lacking? There are not globally accepted or even nationally accepted guidelines. Each DOT has their own guideline. There are some concerns about the environmental impact, how it would perform environmentally, how it will have cement mortars in it, asphalt binders in it, high pH, organic leachate, or also high calcium leachate, high metal leachate maybe with the recycled concrete aggregates especially. And performance-wise, are they going to provide at least equivalent performance of conventional aggregates? And is it, let's say, satisfy environmental impact, perform as good as conventional aggregates, if not better? How would it work with the drainage systems? For instance, RCA is very well known to do calcite precipitation. And how will it impact the drainage systems in pavement systems? And what are the main motivations to do this? Variety of these RCA are, I will cover recycled concrete aggregate and RAP as RCA and RAP. RAP stands for recycled asphalt pavement. And the variety of these materials, you can't really control what is in those RCAs and RAP materials, because who knows what mix design that has been used, what type of cement, what type of binder, and what type of aggregates that are being used, and what type of fly ashes, especially in the concrete initially when it's built, used. I mean, there are studies trying to backtrack these, but there are a lot of there are a lot of information about it, and some lack of correlations, how we can correlate the engineering properties of these materials and how we can do more consistent design and develop construction specs. So one of the main study that I'm about to wrap up with the pooled fund study by National Road Research Alliance, that we try to come up with some results with my colleagues at University of Wisconsin and Iowa State University. We tried to come out, answer some of these questions, and our main goal was to determine the laboratory and field performance of these RCA and RAP materials, looking their stiffness, drainability, and freeze-thaw durability. And on a separate work, not related to this ongoing project that we are about to wrap up, we look into the personally look into the environmental impact of different type of RCAs in terms of pH, leachate, and look into their geochemistry a little bit. So today I will talk about the test sections that were built by Minrod Test Facility, which is a state-of-the-art test facility located in Monticello, Minnesota. That is in western part, that is west of Minneapolis, St. Paul in Minnesota. It has a high volume road test section and low volume road test section, and we have our test sections built on low volume road test section, and you take readings on the outside lane and inside lane on Minrod facility. And basically this is a controlled field test section, which is very rare to get, that everything is tried to be controlled and be specific as much as possible when when engineers build these test sections for us, and we really appreciate and acknowledge their help on this. And then there's a 18-wheeler loading truck that makes a certain number of loops on the inside lane most of the time, and sometimes rarely on the outside lane, to see how the road performs under repeated traffic loads, and take deformation readings and stiffness readings bi-weekly or once a month at least. And I have 11 test sections with other things, but today I will focus on the recycled aggregates based test sections. So we have test sections on that test facility that has all built with 3.5-inch thick asphalt layer on top of a 12-inch thick base materials, with this green base materials where we focus on. We have 12-inch thick coarse RCA materials and 12 base material, and we have a base here, the 12-inch thick fine RCA, and then we have 12-inch thick high quality limestone material to as a control material check to see how this coarse RCA and fine RCA test section works and compared to limestone test section. And then we have another 12-inch thick RCA wrap mixed base layer. And we have a 3.5-inch select granular bottom material that is highly dense sand material. This is kind of used as a working platform to build the base layers on top of it. And the two subgrade here for beneath the coarse RCA and fine RCA are sand subgrades, and the limestone and RCA wrap test sections built on a clay subgrade. And these are some of the pictures of the materials that we have in these test sections. And these are some of the grain size. These are the summary of the grain size distribution of the aggregate materials that we use. Of course, sand subgrade had a very sandy material, and clay loam, as expected, have made predominantly silt and fines content. And if you look at the coarse, fine, and limestone and RCA wrap mixtures, they have kind of fairly close gradations to each other. And here are the summary table, kind of shows the index properties of these materials. And I wanted to focus on that coarse RCA, fine RCA, and limestone and RCA wrap kind of have based on H2 soil classification, have high quality aggregates, A1A, except limestone has A1B, but it still have good quality material. And then based on the unified soil classification system, for instance, coarse RCA is well-graded gravel, while fine RCA means like it has more finer sand and some silt size, finer sand size particles, and silt and clay size particles, not much clay, but silt size particles, not silt material, but silt size particles in fine RCA. And limestone has some silt size particles and predominantly silt, but has some gravel in it too. And on the other hand, RCA wrap mixture had poorly graded sand size particles with some silt size particles in it. So in this field test, we have conducted tests on prior to the construction and after construction. The prior construction, when we are building the subgrade and subbase and base layer, we take a nuclear gauge density readings, dynamic compenetrometer test, which gives us the shear strength of the layers. And then lightweight deflectometer on each layer and falling weight deflectometer before it is paved. Then right after construction, we start taking continuous readings of falling weight deflectometer, which gives us the elastic modulus of the pavement systems, and rotting of the surface, and international roughness index IRI of these materials. Today, I will mainly focus on the after construction FWD test results because of the limited time, but I'll be happy to share other results with you after the meeting if you email me. And here are some examples of LWD, DCP equipment. Again, LWD is the lightweight deflectometer and DCP is the dynamic compenetrometer. And then major main test that we really focused on is the FWD falling weight deflectometer testing equipment. And basically you have these sensors beneath your falling weight deflectometer, and you have the load that you apply at the back of your trap. And then you get these deflection basins, and you can back calculate by using this deflection basin. You can do layered analysis, or by using only the center sensor that you can do. I mean, you again do back calculation, but not through the deflection basin and only through the center sensor. So in these analysis, we did composite analysis first to check to see how the entire system elastic modulus changes with the base type that you use. And then we also try to determine the base and sub-base and subgrade modulus, elastic modulus separately in layered analysis to check this, compare the layered stiffness of these materials with the conventional limestone aggregate. And nuclear gauge density measurements, as you can see, we have these readings both for all top four test sections. White square here is the asphalt layer, so I'm not going to focus on that, but we have the base and subgrade nuclear gauge density values. And as you can see, limestone density is, as expected, is a little bit higher compared to other recycled test sections. But overall, these are the nuclear gauge density results. And then we have the DCPI, the index, dynamic compenetrometer index data. So we done this on a base and subgrade materials, and I will focus more on the base, red solid squares here. And as you can see, what we see, the lower the DCP index, that means your material is very resistive. Okay, so after compaction, prior you paved your test sections, you can see there is not much significant difference with the DCPI values between test sections, even though coarse RCA and fine RCA seem to have lower DCPI value, indicating that they are more resistive, so I have higher shear strength values. Then RCA rep and limestone reps, their average, we take readings on multiple points. So these box plots showing the average and range of these material, the range of the readings. RCA rep and limestone seem to have a compared to reasonably equal DCPI index values. And then we did lightweight deflectometer analysis. Again, I will focus on the base data between these four test sections. And based on this, after compaction, based on the LWD data, elastic modulus of coarse RCA and fine RCA is higher than the elastic modulus of limestone. And RCA rep mixture tend to give the lowest elastic modulus value. And then we look into the falling weight deflectometer analysis. And in this case, the white boxes are showing the modulus of the entire pavement system, while base, sub-base layer, red square shows the stiffness of the layer itself, base and sub-base layers. And again, when we compare these, coarse RCA and fine RCA test sections had much higher elastic modulus than the limestone and RCA rep mixtures. And again, RCA rep mixture provided the lowest stiffness values, even though it's not as significant with its values, that's performance with the limestone material, it's still lower. And these are all before the prior construction. And we also tested, I should, sorry, it is typo, this then this is then this slide should be the after construction. I will fix it and share it with Dr. Reddy later on, and we can circulate these with you guys again. And as you can see, even after paving, again, the coarse RCA and fine RCA test sections perform better when it is paved than the limestone and RCA rep. But once you paved, base and sub-base layers performance kind of become equal to the limestone performance before applying a traffic load. So this was an interesting indicator indicating that sometimes with these mixtures, you may want to focus on the composite analysis. And even in the composite elastic modulus values, as you can see, the coarse RCA and fine RCA were superior in terms of elastic modulus to limestone value. And RCA rep mixtures didn't have, they have the little bit superior on average, but almost identical equivalent of performance with limestone and RCA rep. And another thing with these recycled materials, we wanted to focus on the freeze-thaw durability. And this is a map that kind of shows the 6 climatic regions in the United States for pavement designs. And again, the northern plain of United States has wet, hard freeze, and spring thaw condition, which is the worst condition that you would like to have. Even some, I mean, with permafrost melting now, Alaska's conditions changing and Canada roadways conditions changing, but northern plains are good for soils, are good for farming, but they are not good for building roads. And having this climatic condition, wet, hard freeze, and spring thaw cause significant premature failures to the pavement systems. And that's why it would be good to look into in the field how with over the years, how this freeze-thaw durability and Minnesota test sections are built all the way in the northern part of the United States here. The soil is the same characteristics and it has high freezing and thawing cycles. And we look at these materials and how the coarse RCA and fine RCA samples over the years before for the first freezing period and during the first thawing period and during the second thawing period, as you can see, they overperform. Like in the they really had, they didn't, their elastic modulus didn't change in the first year at all, while the elastic modulus of the limestone and the RCA rep mixture changed with an increase with after the first year of freezing and thawing. However, with the second year, we see some decrease in the coarse RCA and fine RCA materials stiffness. However, it is still much higher than the stiffness of the limestone, original limestone and RCA rep mixtures before they even being exposed to freezing and thawing. And we see a significant drop in the freeze-thaw durability on the limestone natural material here, while RCA rep provides better resistance to this freeze and thaw behavior, even though it's not as good as the coarse and fine RCA material. So overall conclusions, what we come here, RCAs, coarse RCA and fine RCA seem to have better stiffness values, while all of them, including RCA rep, had better freeze-thaw durability at the moment based on this 3 years or 2 years of data that we collected. And then from mechanical suitability, we kind of proved this, that these materials tend to work very well, regardless of their gradation, and even when they are mixed with our rep materials, they seem to overperform the conventional natural aggregates. And the next question is, what is the environmental safety? Are there any environmental concerns, since these are called sometimes waste, sometimes recycled materials? So I didn't run environmental tests on specifically on those tests on the materials that we built those test sections. But before that, I've done a lot of environmental suitable tests on different RCA materials. And we look into the batching, leaching, column leaching, unsaturated leaching. And then we specifically focus on metals and ions, pH, electrical conductivity, oxidation potential, reduction potential, and carbon contents. I will mainly focus on metals and pH today. And these are like, are these RCAs and reps, like I said, they have variety of characteristics. Their particle size changes, their mortar content changes, which will impact the effect of curing times. Their aging, depending on they are stockpiled or they are reclaimed and put in place freshly, these will all change. And depending on the saturation level, groundwater table level, and also precipitation and snow melting, that type of things will impact the leaching of these pH, electrical conductivity, and oxidation reduction potential values. And then how these parameters and also pH will affect the leaching of elements like metals or sulfate, that sort of things. So we've done quite a bit through preliminary analysis on these different type of RCA materials. An initial test list of metals were analyzed, primary, preliminary, and the RCAs that we studied specifically had higher had metal concentrations that above the detection limits were calcium, chromium, copper, iron, and zinc. So our main focus was on these elements leaching from RCAs, and this is a batch leach test method that we use. We'll compact them at the liquid solid ratio 20:1. We rotate them certain RPM at certain time, and we centrifuge them so we can have the supernatant, so we can filter it much easier. We measure the pH, electrical conductivity, and ORP. Then we filter them for metal analysis, and we analyze them for metal analysis, acidify them, run the ICP test for them, and then we also get a separate batch without acidifying them for sulfate, carbonate, and alkalinity measurements, and so on. So we look into the different effects, the effect of curing time, carbonation, and saturation. My main focus will be on effect of particle size and effect of pH on the leaching of elements in today's lecture. But again, I'll be happy to share the papers that we discuss these effects more in detail. So when we look at the effect of particle size, obviously we saw in the mechanical testing portion that the field test aggregate size significantly impact the mechanical performance. Coarse RCA tend to perform better than the fine RCA. Then, of course, due to the remaining cement mortars in these RCA materials, you see high pHs at every level. However, we didn't see a consistent trend in terms of pH, an inconsistent trend in terms of pH. When you increase the particle size, it doesn't seem to impact the pH values of these RCAs. In terms of leaching, though, we didn't see amazing correlations, but we see some trend. The higher the particles sizes, they tend to leach less copper and chromium elements, and this also explains similar trends we observe for the other elements that I discussed in the first table, like for zinc and iron as well. And then we look into the curing time. While with the copper, the leaching tend to increase when your RCA is left in the curing room for a week and for 28 days. On the other hand, chromium tend to leach a little bit more after curing with the presence of more moisture into these RCA materials. And then we look into the pH effect, and to do that, how much we need to determine how much acid needs to be added on each RCA to arrange their pH at a certain level. And then we look into the then we look into when we run these leachate tests, the pH dependent leachate test on RCAs, what type of leaching pattern that we would see. So do we see cationic leaching pattern, the metals leach the highest at acidic condition and have a consistent decrease with an increase in pH, or do we see an oxyanionic pattern that where we see initial high leaching in the acidic condition, then in light acidic condition it starts decreasing, then in the high basic conditions it starts leaching more. And then amphoteric pattern. Are we going to see amphoteric leaching pattern, that you have the highest leaching of the element at acidic and basic conditions and minimum at neutral conditions? And we look into this, and what we see, these are the graphs that shows how the calcium, chromium, and copper leaching occurs within the RCA, 3 different RCA materials when we adjust the buffer their pHs at certain pH levels. With calcium, we definitely see a cationic leaching pattern. With chromium, we see an oxyanionic leaching pattern where we see the highest leaching at the acidic and basic conditions and kind of minimum leaching at neutral pH. And with copper, we kind of see between cationic leaching pattern and amphoteric leaching pattern with majority of the materials. And then, okay, we compare these values with EPA MC, maximum contaminant leachate values. There is none for calcium, but for copper and chromium, as you can see, for copper, as long as you're not at the acidic pH ranges, you're safe in terms of copper. But in terms of chromium, if the pH is around for RCA3, which is a fresh concrete RCA, by the way, not HICA RCA, you may see some chromium levels exceed the EPA limit. However, even if it exceeds the EPA limit, doesn't necessarily mean that it's toxic. What do I mean by that? If you do a geochemical modeling to try to understand the leaching controlling mechanisms and the toxicity level of these leachates, for instance, the chromium seemed to exceed the EPA limits on some of those fresh RCAs at basic pH conditions. It doesn't necessarily mean that it's toxic, because chromium exists in two dominant oxidation states in the nature, chromium 6 or chromium 3. Well, if you consume chromium 6, that will cause significant health issues. On the other hand, when you have chromium 3, it is a necessary nutrient for plants, for people too. So, for instance, some of the wines and beers have chromium 3 embedded in them, and it's a necessary nutrient for human body. So we wanted to determine what is the chromium oxidation state in these RCA materials that we tested. And we run a geochemical modeling with Mintec A2, which is freely available EPA software. You enter your leachate metal concentrations and ion concentrations, pH values, EC values, and then you determine your redox reactions that you wanted to spare. You may enhance the database by adding additional redox reactions. And the speciation analysis tell us that one thing that I want to focus on, chromium exists in +6, which is a toxic form of chromium. So with the chromiums with the RCAs that you use, you want to make sure that you kind of minimize this chromium leaching below the EPA limits to save trouble for everybody. And then this also, geochemical modeling also help us to determine what are the controlling mechanisms of these materials, these elements from these RCAs. And in that, you got your log activity of copper values with their corresponding pH values and put them in a plot. And then you have your solubility lines, like solid lines, tenorite lines here. For instance, here, the solid line is your copper oxide line. Any data point here that stays below the saturation, below this solid line, and it's especially if it's on the saturated line, indicating that leaching of copper is controlled by the solubility, dissolution and precipitation of these tenorite calcium, copper oxide solid phases. And we saw that with the calcium, copper, iron, and zinc are all solubility controlled. However, we didn't catch such a solid line with chromium, and this indicates that chromium is sorption controlled, and we're working on those. And again, these are the two figures that shows how the chromium 6 is not really solubility controlled and sorption controlled. So overall, if we summarize it, RCA materials really provide good geomechanical performances and good freeze-thaw durability. And in terms of environmental conclusions, the higher the particle size, the lower the elements leaching. And calcium, copper, and zinc and iron showed cationic leaching pattern mostly, while chromium showed an amphoteric leaching pattern. And chromium exists in its toxic form, so we need to be careful about this chromium leaching. And all metals except chromium are solubility controlled. And having said that, this is the end of my presentation, and I think we have some questions. How should we proceed, Dr. Reddy?
Yeah. So that's a fantastic presentation, Bora. So you covered a lot of ground. So you can stop sharing the presentation. Mm-hmm. And then now, see the chat box, go all the way to the top. And then, just take your time there's no rush. Just take your time, go down. Anything that deserves, explanation, you can do that. Some of the minor